So this is the next sum that we are going to solve. I have chosen this sum because there are some unique points about this sum, especially what you see over here. See, in this case, this is not only a force, right? There are two forces, but they are being acted upon this beam at a unique position over here. See, so what is this doing exactly? You have to understand this. So because of these two forces, see, this vertical force is going to get transmitted as a vertical force over here. But at the same time, what this is going to do, this is also going to provide a moment, right? So this 40 kilonewton force is acting as a vertical force also, and it is also producing a clockwise moment also, right? Similarly, the 20 kilonewton force, the 20 kilonewton force is acting towards the left direction. So it is in the x direction towards left, and at the same time it is providing a anti-clockwise moment also. So these are the 2 points that you should keep in mind. So with this, we will start solving this sum. Just to save time when solving this sum, I have drawn this diagram already. Okay. So we can start with the summation fx, summation fy, and summation m step, right? So we can say summation fx. So what will be the forces in x direction? See, at A, there will be two forces because A is a hinge joint. There will be force in y direction also and x direction also. So this will be Fay and this will be Fax, right? So summation fx is equal to 0. I can write Fax in the right direction. Then what other horizontal forces? As I said, this 20 kilonewton force is acting in the negative x direction, right? So minus 20, and there is no other x direction force, right? So this is equal to 0. So Fax is equal to 20 kilonewton, right? So we know the value of Fax. Now we can find out the value of Fay and Fd also. Fe, sorry. There will be a reaction force here also at E, right? So we can find out those values. So we over here we have found out the value of Fax as what? 20 kilonewton. So we want to find out the value of Fay also. So we can do summation Fy. So what will be summation Fy? Summation Fy will be first of all Fay in the positive direction, then minus this uniformly distributed load, which is what? 20 kilonewton per meter into 2 meter. So it will be 20 into 2. Then what we have, this 40 kilonewton in the downward direction. So minus 40. Then again this uniformly distributed load in the minus direction. So minus 15 into 5. Then we have plus force in the at point E vertical direction, and we have minus 30 is equal to 0. So these will be all the forces. So with this we can find out the equation. Fay plus Fe is equal to 40 plus 40 plus 75 plus 30, right? So it is 110 plus 75, which will be 185 kilonewton. So Fay plus Fe is equal to 185 kilonewton. So that is the first thing that we get. This we can write this as equation number 1, right? So now the next thing that we have to do is to find summation Ma. Right now, before doing summation Ma, see, what did I tell you? These two forces together are also causing a moment over here, right? So how will we take that moment? How will we calculate that moment? See, imagine that this is the only part that we are currently interested in. Okay, imagine that this is the only part we are currently interested in, and we want to find out the moment about C, right? So what will be the moment about C? It will be this 40 kilonewton. It is rotating in clockwise direction at a distance of what? At this distance is 1.5, right? So it is what? Minus 40 into 1.5. At the same time, what is this 20 doing? 20 is rotating it in anti-clockwise direction. So plus 20, that distance is also C, 1.5. So plus 20 into 1.5. So it will be minus 60 plus 30 which is minus 30 kilonewtons. Means what? It is 30 kilonewtons in clockwise direction. So this means over here there is also a torque of 30 kilonewton meters, right? Now this we can use in our summation MA, right? So summation MA is equal to 0. What will be the forces? First of all, it will be this 20 kilonewton per meter thing, right? It will be minus uniformly distributed load for 2 meters acting at the center 1 meter, then minus 40 into what is the distance, let's see, 2 plus 2 plus 1.5, no, 2 plus 2, 4, so 40 into 4. Then what do we have? I'll just write the distances over here, 2, 2, then 1.5, then here we have 5, here we have 1.5, right? Minus 20 into 2 into 1, minus 40 into 4, then we have that minus 30 also, right? Because it is negative 30. So we will write that also over here. So minus 30 over here. Then we have minus 15 into 5 into that will be 2.54 into 8. See, it will be acting over here, no? This distance will be 2.5. So total distance will be 8. Then plus FE into 10.5 and minus 30 into 12, right? All this will be equal to 0. So what can we write? 10.5 FE is equal to 40 plus 160 plus 30 plus 360 plus whatever that is 15 into 5 into 8, which is 600. So we get 10.5 FE is equal to all this addition, 600 plus 40 plus 160 plus 30 plus 360, which comes out to be 1190. So FE is equal to 113.33 kilonewton. Now we can substitute this FE value in our FAY first equation number 1. So we get FAY is equal to 185, right? It was 185, no? Yeah, 185 minus 113.33. So that comes out to be 71.67 kilonewtons. So we know the value of FAY, FAX and FE. So I can just put over here 113.33. Then we have 71.67, and what was X? This was 20, right? So we know all the values. So the first thing we can do is find out the axial force, right? We can draw the axial force diagram. Axial force means horizontal forces. There are only two horizontal forces. One is at A and one is at C, right? So here it is increasing by 20, right? Then it is remaining constant. Here it is decreasing by 20, minus 20, no? So here, and then it is remaining constant throughout, right? So this is your axial force diagram. So that part is done. Then we can go to our shear force diagram. Okay, those calculations I have written this already just to save time. So to the left of A it will be 0 as there are no forces. To the right of A, see, all remember in shear forces we only consider the vertical forces. So it will be 71.67 over here. To the left of B it will be what? 71.67 minus 20 into 2, which will be what? 31.67. So to the right of B also it will be 31.67. To the left of C also it will be 31.67. To the right of C it will be 31.67 minus 40. It will be 31.67 minus 40. So it will be minus 8.33 Then to the left of D, it will be what? Again, it will be minus 8.33. To the right of D also, it will be what? Minus 8.33. There are no point forces over here. That is why the value is not changing. Now to the left of E, what will be the value? To the left of E, it will be minus 8.33 minus 15 into 5. So it will be minus 83.33. Alright, to the right of E, it will be what? Minus 83.33 plus 113.33. So it will be 30. Right? So to the left of F, it will be 30. And to the right of F, it will be 30 minus 30, which is 0. So we know all the values, we can mark them. On A, it is going from 0 to 71.67. So that is the highest value. So I am just going to delete this. I had just drawn this over here. Okay, just to make it easier. So now we can draw this over here. So shear force goes from 0 to 71.67. I can take each as 20. So 20, 40, 60, 80, minus 20, minus 40, minus 60, minus 80. So from 0 to 71.67, this is the first line. Then at B, what is happening? It is staying at 31.67. So at B, 31.67. At C, it is going from 31.67 to minus 8.33. At C, 31.67 to minus 8.33. What is happening at D? At D, it is remaining at minus 8.33. At E, what is happening? From minus 83.33 to 30. So minus 83.33 to 30, something like this. And what is happening at F? It is going from 30 to 0. F, it is going from 30 to 0. Now between A and B, there is a UDL. So as there is a UDL, it will be a curve, right? So we can draw a curve. There is over here from A to B, from A to B, it is a UDL. So it will be a slanted line. Right, from A to B, it will be a slanted line. From B to C, what is the case? From B to C, no force in between, so it will be a horizontal line. From C to D, what is the case? From C to D, no force in between, so horizontal line. From D to E, what is happening? From D to E, again uniformly distributed load. So what is the first value of E? Minus 83.33. So it will go from here to here, right? From E to F, what is happening? No force in between. So it will be a horizontal line, right? So this will be a shear force diagram. Now that we have drawn the shear force diagram, what is the next thing that we can do? We can draw the bending moment diagram, right? So we can calculate the bending moments. Now you know bending moment at A will be 0. Bending moment at B, what will be bending moment at B? Bending moment at B will be 71.67 into 2 minus 20 into 2 into 1. So it will be 71.67 into 2 minus 20 into 2. So it is coming out to be 103.34. Similarly, what will be bending moment at C? We have to calculate twice because there will be this 30 kilonewton meter moment is at C now. We have to calculate it twice. So bending moment at C will be 71.67 into 4 minus 20 into 2 into 3, right? So that will be that, and the value is 71.67 into 4 minus 20 into 2 into 3. Value is coming out to be 166.68. 166.68. Then what is happening? This is going like this, right? So it will be what? It is pushing this upwards. It is clockwise. It is going to push this upwards. So it will be also positive. So it will be 166.68 plus 30. See, it is going to do what? See, imagine this. And if I am rotating it like this, means this is going up, na? So it will become like this, na? So this is sagging, na? So sagging is positive, right? So that is why we are adding 30. So we get 196.68 to the right of R. Now at D, what will be the case? Sorry, I forgot D over here. So there should be bending moment at D also. So we can calculate bending moment at D over here. I will just zoom out a bit so I can see what is happening at D. So for bending moment at D, it will be 71.67 into 5.5 minus 20 into 2 into 4.5, right? Then what is happening at D? Again, there is at 40 kilonewton force, which is minus 40 into 1.5, and we have that plus 30, right? So this is coming out to be 71.67 into 5.5 minus 20 into 2 into 4.5 minus 40 into 1.5 plus 30. The value comes out to be 184.185. Bending moment at D is 184.185. So what is bending moment at E? So bending moment at E, rather than going through this entire process of the left side, we can just do the simple right side calculations, right? So bending moment at E is going to be what? Negative 30 into 1.5. So it is going to be what? It is going to be negative 45, right? Just the right side calculations I did. Bending moment at F is 0, right? So I can mark these bending moments. Bending moment at A is 0. Bending moment at A is 0. Bending moment at B is 103. See, the biggest value is 196. So nearly 200, right? So we can take 50-50. Each line is 50. So 50, 100, 150, 200, let us say. Okay. So it is what? 103. So somewhere over here. Then at C, it is going from 166.68 to 196.68. From here to here, something like this, right? Then at D, what is the value? 184. So at D, it is somewhere over here. At E, it is minus 45. So it is somewhere over here. And at F, it is 0. So from A to B, what is going to happen? Because from A to B, it is a uniformly distributed load, we have to draw a parabolic curve, right? Then from B to C, what is happening? From B to C, no force in between, so a horizontal line, right? Sorry, slant line. No force in between, so a slant line from B to C. Then at C, what is happening? From C to at C to D, what is happening? Between that, there is nothing. So from C to D, again a horizontal slant line. From D to E, again there is a uniformly distributed load. So there is going to be what? There is going to be a parabolic curve. So we can draw this parabolic curve. From E to F, nothing in between, so a slant line. Like, right? So this is the diagram that we are going to get. See, I might not have drawn this exactly. See, from 103 to 166, there should be considerable height difference between these two, but it is drawn like this. Okay, because you will be drawing on paper, you will be drawing it perfectly. I am drawing on computer, so it is like this, right? So this much part is done. This is my bending moment. What is the extra thing we can do? We can find out the point of contraflexion, XX, right? So rather than taking from the left side, because there are so many terms on the left side, I will take from the right side. Okay, this is just for convenience sake. We will get the same answer from left or right. On the right, there are only two forces to the right of this, right? 30 kilonewton and this reaction at E, right? So I can do like this. See, over here, there is this 30 kilonewton. Over here, there is reaction at E. What was the value of reaction at E? 113.33. 113.33. And what is there extra? There is this uniformly distributed load, right? There is this uniformly distributed load. Let us say this distance is x. Okay, this distance is x. Okay, so rather than calling that distance x, I will just call this distance x, just to make the calculation easier. Okay, that is the only reason. Let us call this distance x. So what will be the terms? See, 30 is doing what? 30 is doing hogging, so it will be negative. So negative 30 into 1.5 plus x. 113 is doing what? 113 is doing sagging, so it will be positive 113.33 x, right? And what is this? This is also going to do hogging, so minus, what is the UDL? 15 kilonewtons per meter, so it will be 15x into x by 2, right? So this is going to be what? This is going to be negative 7.5 x square plus 113.33 x minus 45 minus 30 x is equal to 0. So it will be 7.5 x square minus 83.33 x plus 45 is equal to 0. Now we can solve this in our calculator, right? Mode equation quadratic. 7.5 x square minus 83.33 plus 45 is equal to 0. So I am getting it as either 10 x is equal to 10.54 or x is equal to 0.57 meter. So it is definitely not 10.54, right? This small distance cannot be 10.54, right? From here it will go out of the range only. Possibly yes, it will go just very close to out of range. So it has to be 0.57 meter. So where is the point of contraflexure? The point of contraflexure is at a distance of, this is 0.57 plus this is 1.5 now, from here to here. So this total distance becomes what? 1.5 plus 0.57, which is 2.07 meter. So point of contraflexure is at 2.07 meter from point F. Okay, this is the answer that we are getting.